Vernier Software Technology is proud to support teachers' innovative use of probeware for science and STEM education.
The first thing that I'm going to do is I'm going to draw a picture that represents the moment in time after the bullet has been fired, but before it hits the block. I want to know how fast the bullet comes out of the gun. But we are thinking about conservation of momentum, conservation of energy. So in this first bit where the bullet goes into the block, right? Can I use conservation of momentum? Can I use conservation of energy? Where should I be leaning and why? So I'm going to say exactly what you said with just some different words. The bullet becomes embedded in the block, which means, first of all, that the bullet collides with the block, right? It seems so painfully obvious, but at some point you're going to do a problem and you're not going to know to use momentum, but it's literally going to be like a collision. So think about that, right? The bullet collides with the block, so there's a collision. I should already be thinking about momentum, but I cannot use conservation of energy because when the bullet becomes embedded in the block, they're sticking together. That is a totally inelastic collision. And in a totally inelastic collision, energy is lost, a lot of it.
So when we drop the magnets between these two tubes, we should see a difference in the speed at which they leave the bottom of the tube, right? So I'll drop these in. And we can see that the magnet that traveled through the copper tube was traveling a lot slower than the one that traveled through the PVC pipe. And so we've been talking about magnetic induction for the last few days and looking at the idea that you can induce current in a metal like a copper tube by passing a magnet through it. So if we look at our copper tube and we have our magnet falling through it with the north end pointed downwards, we can imagine the situation at a location at the bottom and a location at the top, right? At the north end of the magnet, the field is pointing downwards. And so as this magnet drops through it, we have a change in flux that's directed downwards, right? Because we're adding down pointing field. And so what's gonna happen is that we will create an induced field to counteract the change in flux, and that always has to be opposite. So our direction of being induced will be up. My thumb points up by right hand rule number 3, and then my fingers curl the direction of current. So we're going to create current that's going that way at that location. And now we have an upward pointing north field that will interact with that down pointing north field, right? North on north will be a repelling situation, so it slows down the magnet.
This is about reproduction. It's about making more cells, especially bacterial. Many bacteria, they reproduce through a process called binary fission. So us, being mammals, being animals, we reproduce sexually. It takes both an egg and a sperm in order to reproduce. But not all organisms have to do that. Bacteria and some other things, they can clone themselves or go through a process called binary fission, where they just simply make copies of each other, of themselves. Okay? It's an identical clone. So I can mimic that by taking a little piece of my string again, a longer piece this time. Okay? So I've got some string here. I'm just going to try to mimic binary fission. So I'm going to blow a bubble. I'll put this camera down here. I'm going to blow a bubble. Make it a nice size. Ooh, did you see I had a gap junction there? Make sure the bubble's in the screen. Wrong way. Then if I take my string, go through the bubble underneath, pull it up, look, now I've got 2 bubbles. And go this way. Killed it. Let me get this out of the way. This is a really cool demonstration that shows you how a bacterial population can grow so fast. Watch this. From 1 It goes through fission. Then we have 2, and they go through fission. They have 4, and they go through fission. You see, if I just keep doing that, I end up with lots and lots of cells in a really short amount of time. Lots and lots of bubbles. Think about this as a zygote, too, an egg that gets fertilized by a sperm. It's just a ball of dividing cells. It's kind of like this. It's just like, it'd be more of a cluster, a bunch of a ball of these cells, but kind of the same process. I mean, just splitting, just copying. You can see quickly how a bacterial population could grow quite quickly. So you see, I had 1 cell, and now I have lots of cells. That's it. That is cell concept 6. Lovely. Which says that many bacteria reproduce through binary fission. Put that in your own words. Describe how I used bubbles to model the cell concept. Okay? Hope you enjoyed. Hope you learned something. Tomorrow back in class, we'll be going over this test review. Testing procedures in this class, okay? You got it. You got this. Okay. Keep your note binder, and I'll check your binders on test day. Bye.
Yeah. We're going to continue with our discussion of resonance. One thing everyone likes to do is sing in the shower. And this problem addresses why it's so much fun to sing in the shower. So we imagine a shower stall here, and we have a height of about 2.45 meters, a height of about 8 feet. And that height selects what the resonant wavelength is, what the primary wavelength is, the fundamental frequency for a sound wave in that shower. So when you get in the shower, you go, ah, it comes at you at a certain fundamental frequency. It comes back at you. What is that fundamental frequency? When we divide these numbers and multiply, we get a fundamental frequency of 70 hertz, 70 cycles per second. But of course, you don't hear only one frequency there. Remember with the fundamentals that you hear the multiples, integer multiples of the fundamentals. You also hear the harmonics there. So we hear 70 hertz, 140 hertz, 280 hertz, and so on.
Congratulations to all of this year's award recipients.